Today's screencast is going to be about acids and bases, and you should have some general background knowledge from 8th grade physical science if you were in the Hanover School District on acids and bases. So from our other chapter, you should be able to tell me what the formula of an acid is. Okay, I'm going to tell you there are different definitions of an acid, but we're going to start with the most basic definition. It's a compound starting with hydrogen. And you might remember from doing your formulas, they have general HX, and they're always aqueous. Okay, so they start with hydrogen, so this is the general formula. And I didn't create a worksheet for this, so you're going to have to just kind of jot these notes down. You are expected to know this information. And they release hydrogen ions in water. So you might remember from doing net ionic equations, HX would give you hydrogen ions and then whatever other ion it was. So if it's hydrochloric acid, it's going to give you hydrogen ions and chloride ions. If it's phosphoric acid, it's going to give you hydrogen ions and gives you 3 of them, and it gives you phosphate ions. Okay. Okay. Next thing I'd like you to write down in your notes are some general properties of acids. They are corrosive, which means they can be damaging to objects that they come in contact with. Okay, most common corrosion you might be familiar with is rust. If you put iron in an acid, it will rust much more quickly than it will in air or in water. Okay, you might have had a personal experience with this. If you ever vomited, that burning sensation in your throat is from the acid burning that skin, which is not protected. So your stomach has a special lining that protects it from the acid, but your esophagus and your mouth don't have that, and that's why you get that burning sensation when you vomit. Okay, so not all acids are equally corrosive, so we look at a property called pH, and they have a pH value less than 7. Okay. I'm going to spend some time talking about this pH scale before I go on to bases, and then we'll of course talk about bases in terms of pH as well. So you might notice that the pH, the H is capitalized and the P is lowercase. Usually when we write something that's capitalized, it's the capital letter first, but it might ring a bell that acids start with hydrogen, and this has something to do with hydrogen. So literally pH means the power of the hydrogen. Okay. And again, I capitalize that just for emphasis, so that's why that is always capitalized, because it relates to that. So pH is equal to the negative log of the hydrogen ion concentration. So that represents concentration. And probably most of you have not had much with log functions. But if I had 1 times 10 to the negative third, and you use your calculator log button, so it's going to be log. If you take the log of 1 times 10 to the negative third, so you take the log of 10 to the negative third, you're going to get negative 3, and then if you make that negative, so negative log of negative 3 is going to be a positive. So that's where the pH would come from, is that value of 3. Okay. Generally, pH scale goes from 1 to 14, but you can have values that are less than 1 and values that are higher than 14, but those are extremely strong acids and bases. And it's alphabetical, so just like you're counting, we start with 1, the acids come first, the bases come last. Now, the only thing that doesn't fit in this alphabetical thing is 7. So 7 is the neutral point, so if it's not an acid or a base, it's going to be 7. Okay, so if you remember, we did the log of 3. Okay, each one of these is a power of 10 difference. Okay, so a pH of 7 is a hydrogen ion concentration of 10 to the negative 7th, and we'll drop the 1. A pH of 6 is an H plus concentration of 10 to the minus 6th. Remember, that's a negative log thing. So pH of 5 equals an H plus concentration of 10 to the minus 5th. So each time you move, this is 10 times more acidic. Okay, and if we go from 7 to 5, that's 100 times more acidic. Okay. And if you would go from like 7 to 3, so a pH of 7 to a pH of 3, if you look up here, you're going to move 1, 2, 3, 4. It's going to be 4, not just 4 times, it's going to be 10 times 10 times 10 times 10. So moves 4 powers of 10. Okay, or 10 to the 4th, and 10 to the 4th equals 10,000. Okay, again, count your zeros. So this is 10,000 times more acidic than a pH of 7. So that's something to keep in mind. So it is kind of a big deal when you go from one pH unit to another. It really is increasing the acidity more and more. Okay, for the next one, we're going to look at going the opposite direction. So if I'm going this direction, it's more basic. Okay, if I'm going this direction, it's going to be more acidic. So if I'm going from 3 to 8, going from a pH 3 to pH 8, 8 minus 3 is 5 place values, so I'm going to have 10 to the 5th. So this is going to be 100,000, so I'm going to add 5 zeros, 1, 2, 3, 4, 5. So a pH of 8 is 100,000 times less acidic than a pH of 3. So that's important to note. In the reading that you did, you should have a list of things that are in your daily life that are acids. So you might want to jot some of these down. Things like orange juice, your blood is acidic. All rain is, whether it's acid rain or not, so normal pH of rain makes it acidic. Okay, soda, all of those things that they worry about with your teeth, they're going to react with the enamel in your teeth and actually dissolve that, so it's actually corrosive to your teeth. So that's another reason why acids aren't good for you in large quantities. So again, your orange juice has some nutritional value, so I wouldn't avoid that, but it's another reason to avoid sodas. Okay, we haven't looked a whole lot at bases. I probably may have mentioned this throughout the year. But bases, the chemical formula ends in OH. Okay, so you're going to have some general formula, so some cation, and I'm just going to call that Y with OH, so that's going to be a cation, so any positive. So something like calcium hydroxide would be a base, sodium hydroxide would be a base. And again, there are other definitions of base, but again, we're going to keep it simple. Okay. Okay. Bases also dissolve in water sometimes, so this you're going to have to use your solubility rule for hydroxides, but most of the ones that we're going to work with are going to be soluble. Okay, another term that's used for bases are things that are alkaline. So I'm sure all of you have heard of battery acid. So most car batteries, boat batteries, motorcycle batteries, those kinds of things are acid-based, but you've probably heard of alkaline batteries. So your dry cell batteries that you use in electronics, so things that are in, nobody probably carries these around anymore, but if you have like a, little portable music player, I know no one has those anymore, but some flashlights have, those kinds of batteries. I have dog collars that have them. We have an underground fence for our dog, so that's an example of one. So I have games that, you know, have little batteries in, so you might have younger brothers and sisters that have games that they still play with batteries. So when you buy a Duracell or an Energize type battery, those are all alkaline, which means they have a base inside them. So bases, their general properties are going to be a little bit different. We use the term caustic for bases, okay, but do the same thing. Caustic means it causes damage. To things it contacts, so you might know if you leave a battery in long enough, those bases will corrode or basically eat through the metal casing of the battery. So we call it corrosion, but it's really more of a caustic situation there. Okay, probably one of the two most dangerous things that you have in your home is a very strong caustic substance, and it probably says this right on the label. If you have oven cleaner, that one's very caustic, or the other one that's right up there are drain opener. Those two things are very, very basic and very, very hazardous. You might remember from the demo I do with the egg at the beginning of the year with lab safety. Bases are the things that made the egg become like a solid, so you want to be very careful when you're using those products. And these guys have a pH greater than 7. Okay. So if we look at the scale at pH again, if you get your higher numbers, so let's say probably anything greater than 10 are considered strong bases, anything probably 2 or less are strong acids. Okay. So 5 and 6 would be weak acids. Okay. 8 and 9 would be weak bases. Okay, and you'll see that they're opposites. When you put them together, we call that neutralization because they cancel each other out. Okay, and I'm going to say neutralization doesn't necessarily make things completely neutral, but it does move the pH closer to 7. So you might have something that's 2 reacting with something that's 10. That gets you to 7, but you could have something that is 2 reacting with something with 9 that would be less than 7. So they mix it closer to 7. It won't necessarily always be 7. So it depends on concentrations of the acids, so how much of each you put together. So just because you try to neutralize something doesn't mean you completely wipe out if you don't have enough of either chemical. So that's going to be the next thing that we're going to be looking at is neutralization, and this is on the back of the worksheet that you already have with acids on it. So, okay. In a neutralization equation, you're going to have an acid plus a base, and you should be able to identify the acid by the H in its formula and the base by the OH in its formula. And essentially what happens, you'll see in the next example, or the second example here, I no longer give you the formulas for the products, so you're going to have to come up with that. So basically H and Y are switching places. So Y is going to always be your positive, and we always write positives first and negatives second. Okay. And again, you're going to have to use your rules for writing formulas. Salts are ionic compounds, so this is going to end up being ionic. Okay. So you'll have to do your crisscross and reduce, or your least common multiple, in order to figure that out. And then you're going to have H and OH together. So remember, that's water, H2O. So again, we're kind of looking at it from its structural, or its Mickey Mouse. So this is the first hydrogen, that's the oxygen, and this is the second hydrogen and the hydroxide. So if you write it this way, it's much easier to balance the equations, and you actually see those things being formed. So another way of looking at this is kind of like boy 1, girl 1, boy 2, girl 2. So again, in ionic compounds, we don't have any girls together or boys together. You have a metal and a nonmetal, so it's one boy, one girl. So what you're going to end up with then is these two boys are going to switch partners, or the girls are going to switch partners, however you want to look at it. You always get water, so that's the easy part of the formula to write. So boy 1 is going to then end up, which is the hydrogen, is going to end up with girl 2, which is the hydroxide, and boy 2, and we always write the boys first, sorry ladies, and it's going to end up with girl 1. So you're just seeing again that you're basically reversing the hydrogen and the sodium. Now, the thing that you always want to check are charges. So for the salt, so sodium is a +1, okay, nitrate is a -1, so I don't have to do anything with the formula there to crisscross and reduce. Okay. For the second one that we have here, hydrogen and calcium are going to switch places, and it really doesn't matter what order you do this in. So you might say, gee, I know it's always going to be water, so I'm going to write that first. So this is hydrogen, okay, with hydroxide, and then I'm going to have my Y value, or my second boy, is going to be calcium with nitrate. Okay. Now again, I have to check charges, so if you go to the periodic table, calcium's in group 2A, so it's +2. If you look on your ion chart, nitrate is -1. So if I crisscross or reduce, I'm going to get CaNO2 taken twice. Okay. And I do have to balance my equations, so I have two NO2s, so I need a 2 in front of the HNO2, and that'll give me 2 hydrogens, and I need 2 hydrogens, and again I'm balancing it, the first hydrogen with this, and then the OH group with this. And you'll see I have 2 OH groups here, and this 2 distributes here, so I have 2 OH. Now, it's not incorrect. Chemicals don't have egos, so they don't care who gets written first. Okay, I could start with calcium with nitrate and do hydrogen with hydroxide. Now, if you really want to get particular to charges, you could do +1 and -1 with the hydrogen and hydroxide. They're always going to cancel out and give you that formula. But it's very, very important that you check your charges for calcium nitrate. So again, this is your salt, and this is your water. Okay, again, needs to be balanced. So this tells us I need twice as much acid as I do calcium hydroxide to neutralize this. So again, if you had equal volumes, you wouldn't be completely at 7 because you wouldn't have enough hydrogen. And we're not going to get into all the particulars like that, but I just want you to understand that just because you put an acid base together, it depends on this mole ratio that we have here, how many molecules of each you need to neutralize. So equal volumes don't actually always get you exactly to a pH of 7 for this. Okay, so there are several examples there for you to try. Please complete that worksheet right now and check Firefly for a due date.